All right, so while using tables is great, and we will use tables extensively, there are other ways to get pressure, volume, and temperature data. You could do that with models, so with empirical models. And you've seen this in physics and in chemistry, specifically with the ideal gas law. It's not a law, it's just an empirical formulation that we've created to relate P, V, and T. And let me review that really briefly, and then we will take off and use it for our purposes. But basically, the idea was for the ideal gas model that gas molecules don't really, quote unquote, see each other. And when they go past one another, they just kind of go through one another. They don't interact, they have no molecular interactions. That proves to be pretty bad approximation of what gases actually do, but it gives us a good direction. And so people use it to kind of understand overall interactions, and we will do the same. We will use ideal gas models specifically in this class because it's one, easy to use, and then two, it's not so hard to extend this to other models. Okay, and I will show you other models in a few minutes. But let me focus at the moment for the ideal gas. Okay, and we can. I mean, I'm saying it's a bad model. It's not horrible. It just has a high level of error in it. But by and large, for many gases, it gives us correct trends. So at least we can get some sort of quantitative treatment that is reasonable. May not be accurate, but it's reasonable and gives us an understanding of how things work. So from Gen Chem and from PS 160 that you took, which is physics 2, you learned that PV is equal to nRT, okay? And pressure, volume, and then we have the moles, and then R, and then temperature. And I'll go over the R in a second again. It's the universal gas constant. In our class, we rarely specifically talk about moles or masses. We usually use specific quantities. So if I divide through the ideal gas equation by N, I can just say it's P times the molar specific volume is equal to RT. So far in our examples and in the tables and everything that we've done, we used V bar. And V bar is specifically volume divided by mass. I'm going to use V hat to be the volume divided by the number of moles, okay? We will not use that extensively, and we will try to convert to V hat as quickly as we can. You could also use the ideal gas specifically like this, as PV bar is equal to RT times MW, which is the molecular weight. And to remind you, to get the molecular weight, you do need the periodic table, and you just add up the number of the atomic masses corresponding to the chemical formula that's there. So, for example, H2O, H, if you look at the periodic table, has a molecular mass of 1, and O has a molecular mass of 16. There are two H's, so that'd be 2 times 1, and then one O, which is 16, so there's 18 molecular weight. That's the molecular weight, and the units for it would be grams per mole if we're using the SI system, or which I'll show you in a second what happens. I could use pounds per pound mole, and I'll show you that in a second. So worry not. Okay, so I could use that specifically to get specific state variables directly from this equation. I can also use the ideal gas to see how things change from one state to another. So if I'm assuming in the mass analysis, the control mass analysis, that the mass does not change, then I can just cancel out that N or the M or whatever, and I could say that for state 1, P1 V1 divided by P2 V2 should be equal to T1 over T2. The mass really shouldn't change, so I can cancel that out. So that's kind of how that would work. So you could use it in this form, or you could use it in the regular form. We rarely will use it as PV equals an RT. Okay, this R thing, ignore this little U thing, pretend it's not there. There are many ways to define R. And it's just a unit-based type thing. And if to remind you from general chemistry, R was just put there to be a fudge factor. So we wanted to have a nice linear variable equation relating P, V, and T. And when we plugged it in, we saw that there was a constant that was there. And to make this work, we just used it. And so depending on your system, on your units, specific units, you can select the R that corresponds to it. So if I give you a question that's primarily in bars and meters cubed, use this one. If I'm giving you a question that's primarily in BTUs, use this one, etc. So kind of, we're going to have that kind of framed somewhere in a reference sheet, so you have that. If there are other R's that you find useful in problem solving, slap them in there so you have them. I do want to talk specifically about this mole business. So in general chemistry, extensively you use moles, and those are defined as gram moles for the SI system. And what that would mean, okay, that if I have 1 mole of, let's say, water, we just talked about water. Water has a molecular weight of 18 grams per mole. So if I have 1 mole of water, that just happens to weigh 18 grams, okay? If I have 1 mole of hydrogen gas, that happens to weigh 2 grams. Okay, and the reason that hydrogen gas weighs less is because hydrogen has a lower molecular weight, okay, for the same number of molecules. It just has a lesser molecular weight, and therefore it will weigh less. That's great, and we use that for the SI system specifically. So the mole that we've discussed so far, the mole will give you a gram based on the molecular weight that you see on the table. Pound mole, it's the same nonsense. It's the same exact concept, but instead of giving you a number in grams, it gives you a number in pounds. So it's exactly the same thing. There's no change in concept. It's just that the unit changes. So hydrogen, which we determined the molecular weight for, is 2. In the SI system, 1 mole of hydrogen would weigh 2 grams. In the customary system, 1 pound mole of hydrogen would weigh 2 pounds. Okay, it's just basically a conversion, converting from grams to pounds. That's really all it is. There's no change between it. So if you look at a pound mole, if you want to convert from a pound mole to a gram mole, all you got to do is use the conversion factor between a pound and a gram, and then you get that. Okay, so it's not complicated. It's just weird and sounding, but you could easily use that. Okay, so let me show you the internal energy in the enthalpy. So the internal energy and enthalpy are not directly measurable quantities. I cannot stick that into an internal energy meter and get the internal energy of a system. I cannot put a system and get its enthalpy directly, specifically. So what we're going to do is we're going to have to indirectly measure it using PV and T data, which are measurable. So let me just remind you from, I guess, Calculus 3, for a total derivative of a function that's dependent on 2 variables is defined as this. It's basically the sum of the partials. So I could take the derivative of the function with respect to one of the variables and pretend like the other one is a number, and take the derivative of that same function with respect to the other variable and pretending that the first variable is a number, and then I add them up and that gives me the total derivative. And we write it like this. And to remind you what this means that I take my f, whatever f is, I take a derivative with x, I pretend y is a number. Okay, so this means take a derivative of x, hold y constant, times dx, and then take a derivative of with respect to y, hold x constant dy. I add them both up and I get the total derivative. Okay, so it's customary in thermodynamics to relate U to specifically T and the specific volume, and H to P and T. So I'm going to basically look at this. I'm going to translate this into U and H for us. So I'm going to replace this F with a U and look at what DU would be. And I'm going to look at DH. And when I do DU, instead of using X and Y, I will use T and V. When I use H, I will use P and T. So let's look at that. So I'm looking at du, and I'm going to take a derivative of u with respect to t holding v constant dt, plus du dv holding t constant dv. Okay, so that's the total derivative of u. And I'll do the same thing for h, but the natural variables for h would be t and p, so it just looks like that, just math mumbo jumbo. Turns out that when I take the derivative of u with respect to t holding v constant, that quantity is measurable, and that's known as the specific heat with constant volume, CV. And this thing is also measurable, and that's known as CP, which is specific heat with constant pressure. So those, the green and the blue, they're measurable variables. So I could find them. And then the other thing, turns out that for an ideal gas, those go to zero. And we could prove it, but and I could show you how to do that. But for now, just take my word for it. Those go to zero for an ideal gas. For non-ideal gases, they do not necessarily go to zero. So what that means is that for an ideal gas, I can calculate du. du would be equal to CV dt, and dH will be equal to CP dt. And let me remind you what this specific heat thing is. And, you know, we also talked about that in general chemistry and also in PS 160 and physics 2. Specific heat is how much energy I have to put into the system to raise 1 gram 1 degree Celsius. Okay, so you can measure that. You can take a cup of water, you weigh exactly 1 gram out of it, and then you can raise the temperature by 1 degree Celsius, and all you gotta do is measure the amount of energy you put into it, and that gives you specific heat. So that's something you can get. And so you can find the specific heat for different substances, and we have them in the back of the book, okay? What's different in this class, what you're accustomed to, is that CP and CV do change with temperature. You see how it says CV? V is constant, not T. And here, P is constant, not T. So they are functions of temperature, meaning that water at 95 degrees Celsius and water at 25 degrees Celsius have different specific heats, which makes sense. I need less or more heat depending on what the temperature of the substance is. So there are ways and there are functions that show you the dependency of the specific heat with temperature. And we will use them because once I replace CV, let's say CV, for example, I'm just going to throw a thing that's not really true. Let's say CV is 2T plus 3, whatever. Then I can put CV here and I can integrate that because I know 2T plus 3, 2T is dependent directly on temperature. I can integrate 2T. 2T integrated is just T squared, and 3 integrated is just 3T. And then I just plug in the initial and final temperature, and I get my du. So that's what we'll do. We're gonna put like an actual thing in here and calculate du and calculate dh. So we can do that, and every substance has its own, and I will show you in examples what that looks like. Okay. So we can also define the ratio of CP to CV. That's going to become kind of handy when we talk about polytropic systems as K. So K is equal to CP divided by CV. It also turns out that for an ideal gas, CP minus CV just happens to equal to R, which is the ideal gas constant from before. You know, that 8.314 or whatever, 0.08206, all these things, depending on your unit of measurement. You can take, if I know the CB of an ideal gas, I can get CP with R. So in an example, I may give you CB is equal to 3 or something, and then you can find CP from this relation. If I don't tell you what the gas is specific, I just say an ideal gas, blah, blah, blah. I give you a CB and you need CP, you can use this relation to find CP. Okay. So let's summarize for an ideal gas. I know that PV is equal to nRT, which we're not going to use much, but we are going to use PV hat is equal to RT, or PV bar is equal to RT times the molecular weight. We know that DU is CBDT. We know that DH is CPDT. We do know that CP and CB are related this way. For work, which I did not specifically show you here, but you do know that work for anything, that's not for an ideal gas, work is the integral of PdV, okay? If I hold P constant, I can just take it out of the integral and it'll become P delta V. If I hold T constant, okay, what I could do is, look, I have this P here, and if you want to derive it yourself, go ahead. If I have this P right here, I can go here, or here, or here, whatever I want, isolate P, and throw that in here. So let's say I take this thing, PV is equal to nRT. So P is nRT over V. And if I put nRT over V here, okay, then I have an integral with respect to V. If T is constant, I could take nRT out of the equation. So I do, out of the integral, I'm sorry. Then I have the integral of dV over V, and that's just ln of V. And I evaluate that from the initial to the final volume, and I get nRT ln V2 over V1. So that's going to come in handy when I have isothermal conditions. That's going to come in handy when I have isobaric conditions. And when I have isochoric, as in no volume change, that goes to 0. So we're going to use that as well for the ideal gas. So let's do some examples related to that.